Hi, my name is Mario, and I will be talking about software and hardware co-optimization on the IPU, an MLPerf case study. I will start with an introduction. Next, I will talk about an algorithmic perspective called packed BERT. Next, I will talk about a software perspective on parallelism and recomputation. Then I will talk about other features, including hardware-related features. Finally, I will come to a conclusion. This year, Graphcore participated in the MLPerf benchmark. MLPerf is a benchmark for machine learning and hardware. In this benchmark, we showed amazing results on BERT as well as on RESNET 50. This talk will give an insight into software features that we used to obtain those amazing results. Let's first talk about the IPU. The IPU is a massively parallel MIMD architecture. It supports FP32, FP16, and most importantly, FP16 with stochastic grounding. The IPU consists of 1,472 independent IPU cores. Each of them can have 6 independent worker threads. The in-processor memory of the IPU is 900 megabytes, and there's a very large memory bandwidth per IPU. As you can see in the left figure, 4 IPUs are combined in the IPU machine M2000. The IPU machine also comes with a slot for DDR4 DRAM. 16 M2000s get combined in a POD64. The POD64 is a network-based disaggregated architecture for host versus IPU resources. That means, depending on the workload that we have, we can adjust the amount of host processing. All the M2000s have special connections to allow for a fast communication between the IPUs. If you want to know more details on our hardware, I strongly recommend to visit the Hot Chips presentation by Graphcore CTO Simon Knowles on our blog webpage. For our MLPerf implementation, we use the full stack of software and hardware co-optimization. We use the algorithmic part with packed BERT. We use the software part by using parallelism and recompute. And we used hardware features like FP16, stochastic grounding, and low batch size. Let's start with the algorithmic improvement, packed BERT. The motivation is that when we look into the BERT model, it's a transformer-based model with a bidirectional encoder with self-attention. So for efficient use of the ALU on the hardware, it is required to have batching, and for having batching, we have to pad the samples to the same length. This is a trade-off between wasted compute for speed up from the parallelism. But the question is, how much compute are we actually wasting? Here comes the answer. In looking at the data, we realized that in Wikipedia, if we use a max sequence length of 512 when generating the BERT dataset, a lot of the samples are more in the range of around 100 sequence lengths. So in total, we are wasting 50% of compute because 50% of our data are padding tokens. Only 23.5% of the total data actually have the length 512. All the other sequences are shorter. Is this specific to the Wikipedia dataset? No, it is not. We looked into different datasets and we realized that the squat dataset as well as the glue datasets all have a skewed distribution in sequence lengths and thus require an excessive amount of padding. So, how do we get rid of the padding? Our approach we call packing, and it consists of 3 core steps. First, we have to pack the data. This means we have to concatenate sequences. Second, we have to adjust the model to process the data correctly. Last but not least, we have to adjust the hyperparameters. How does packing work? Packing n sequences is an NP-hard problem, even when we're combining 3 sequences. So, it's impossible to do it efficiently on raw sequences. Thus, we use histograms of sequences. We developed 2 packing algorithms. The first one is the online shortest pack first histogram packing algorithm. You can see it in the video. First, the data gets sorted by size. Then we start at the longest sequence and go step by step down. If we find a sequence that can be combined with another sequence, we put it together and resort until there's nothing to sort anymore and to pack anymore. In the offline, non-negative least squares histogram packing, we cast the problem to a mathematical optimization problem and solve it with a standard non-negative least squares solver. This is explained in the following animation. Next, we have to adjust the model. The mandatory part of the adjustment is that we have to adjust the masking. So instead of masking out only the padding tokens, we avoid in our masking approach that different sequences can attend to each other. Additionally, we have to adjust the positional encoding. Depending if NSP is used or not, we have to also adjust the respective loss calculation. Therefore, we developed a vectorized unpacking algorithm that can cast the problem to a sequence-based evaluation. Last but not least, we have to adjust the hyperparameters. There are 2 main hyperparameters we have to look at. The first one is the learning rate. We realized that adjusting the learning rate didn't help us, so we're keeping the learning rate as is. However, another set of hyperparameters is related to LAMP. LAMP is a standard optimizer used in BERT. When we calculate the weighted moments M and V for LAMP, we have weights that combine the old moments with the new moments. These weights are called beta. These weights for moments have to be adjusted. And we realized that there's a very simple heuristic to actually adjust them. Therefore, we need the packing factor. Packing factor means how many sequences are on average combined in one sequence, in one new packed sequence. So we take this packing factor and just take the weights to the power of this packing factor. So, how does it look in the experiments? In this table, you can see the performance of the two different packing algorithms on the Wikipedia dataset. The first line shows you the baseline. Without packing, we have 50% padding. If we enable a larger packing depth, that means allowing to combine more samples together, we get a better efficiency, up to 99.75%. The best performance we achieve with the offline NN-LSHP algorithm. You can see we get a packing factor of almost 2, which is very, very close to the optimum. Additionally, we looked into how much overhead do we have from the processing. Remember, we adjusted how packed sequences get processed. The overhead is a little bit more than 4% and doesn't increase much with the packing depth. If we combine the overhead with the packing factor, we can calculate how much speedup we will get. In this case, our best speedup would be 1.9. So the question remains, do we get these results in practice? And the answer is yes. Yes, we get 2x speedup. If we look only at the flops, the effort is actually only reduced by a factor of 1.913. However, we have less overhead of I/O. Putting everything together, this leads to an additional speedup which pushes us beyond the 2x. This can be seen on the right graphic. If you have any further questions on packing, please read the blog and the paper, as shown in the links. Next, we will talk about hybrid, model, and data parallelism and recomputation. This is the software perspective. And a very important ingredient is the host disaggregation. BERT is not host-bound. That means that one host is sufficient even for 64 IPUs. This comes with power and cost savings. BERT combines model and data parallelism for job distribution. For the pod 16 setup, we do the computation on one M2000 for a model and then apply data parallelism. So, how does our pipeline look like? How does the model parallelism look like for BERT? This is displayed here for the forward pass. On IPU 0, we have the embeddings and 3 encoder layers. IPU 1 then continues with 7 encoder layers, IPU 2 with another 7 encoder layers, and then IPU 3 with the last 7 encoder layers. Afterwards, the data gets sent back to IPU 0, where we can calculate the projection and the losses. The reason for sending it back to IPU 0 is because it has the embedding layers. How do we process this model parallelism? We use a pipelining scheme. Pipelining is supported over our pipeline API, which we have in TensorFlow, PyTorch, and our popular advanced runtime called PopArt. We start the pipeline with a forward pass on IPU 0. The data gets sent to IPU 1 and processed there with a respective forward pass, while IPU 0 is processing the next batch of data. This continues until we're ready for a backward pass. Then we group forward passes and backward passes. To save memory, we recompute the local forward passes F1, F2, and F3 as part of the backward passes B1, B2, B3. To scale this approach to an IPU pod 64, we combine it using data parallelism. Data parallelism is supported in all frameworks, and it only requires specifying the number of used IPUs. So that means we have model parallelism on sets of 4 IPUs, which first process a forward pass, then we have the backward passes, all in a pipeline fashion, and eventually we average all the gradients together and then start again with the forward passes. Another important software feature is replicated tensor sharding, or short RTS. We use it to reduce the overall memory footprint. It can be combined with variable offloading to our streaming memory, and it's our path for even larger models. So how does it work? In the normal approach of data parallel processing, we have the optimizer states, the gradients, and the parameters on all the replicas. In replicated tensor sharding, we distribute the data over the different replicas and thus save memory, which can be used for processing or for processing larger batch sizes. For example, we could chart the optimizer states, having the first part on the first IPU, or better to say, on the first replica, and then continuously having the other parts of the optimizer states distributed. The same can be applied, for example, to gradients and optimizer states, or to parameters, optimizer states, and gradients. Note that for the most time of the processing, the optimizer states are not needed. So sharding those gives us the best benefit. So which other features did we use? One important ingredient of our submission was the use of low batch size training. A large local batch size requires storing plenty of unused activations. For BERT, we used the local batch size of 2. To simulate a larger global batch size, we can use gradient accumulation, and so we can save update costs by not updating every 2 samples. Another important ingredient is low precision training. For MLPerf, we trained with FP16 precision, and we used stochastic rounding. The weight aggregation happened in FP32. However, the master weights were kept in FP16. Also, the lamp moments were kept in FP16 and streamed from the DRAM on demand. So far, we mainly talked about BERT. Let me tell you how our RESNET 50 setup looked like and what is worth knowing about our RESNET 50 setup. For RESNET 50, we used a single IPU data parallel setup with 1 to 4 hosts. We introduced a convenient recomputation API in our TensorFlow 1.15 framework to boost the batch size to 20. Why were we interested into a batch size of 20? That comes in the next part. For calculating a batch norm, it is required to have statistics of at least 32 samples. Hence, we combine the data from 2 IPUs for a sufficient batch size of 40 samples. The distributed batch norm can be activated by a user with a simple configuration variable. To conclude, we applied several software strategies to get an amazing performance in MLPerf. Our strategies are not benchmark specific. They generalize to a variety of models and datasets. Our software comes with an intuitive support for hybrid data and model parallel training, including recomputation in TensorFlow. Last but not least, I recommend try PACBERT to accelerate your NLP application. Thank you for your attention. We are always looking for new applications. We are hiring.